Cool. Whenever you are ready, you can start sharing a screen.
Right. Give me a second. So I think I need to quit and reopen to share the screen. So just give me a second.
Is there any issue?
Okay. He needs to quit and reopen because the live was.
Okay. Eh? Acha.
I think he left.
No, yeah, he left. He's joining again.
Okay, you see me?
We can see it. We can see it.
Okay, whenever you're ready, I can start.
Yeah, we are ready. You can start, bro.
Okay, cool. So yeah, first of all, thanks for inviting me. I'm Enrico Bottazzi. I work as a cryptography engineer at PSE, and the topic of today's presentation is verifiable fully homomorphic encryption. So the outline of the presentation is that we're gonna start with an application that is powered by FHE. We're gonna then, starting from the application, abstract a model, a sort of mental model about what is possible, what you can build with FHE. And starting from that, we're gonna also see why we need verifiable fully homomorphic encryption. And eventually, I'm gonna explain this ZK-FHE gadget that is able to allow verifiable fully homomorphic encryption. So we're gonna start with the application. It's something I think is pretty, it should be familiar to you. So it's like a dating app that is based on music. So we simply want to match people based on their music preferences. And we want the music preferences to be private. So I think this is a kind of a different type of privacy. It's not like privacy against like big corps that want to use their data. I mean, I don't think people care that like Spotify knows my preferences, but it's more like an intimate thing. Like I don't want my friends, my kind of partner to know my preferences because I suppose this is like an intimate thing, and I actually had like an experience like meeting someone that didn't want to share the like Spotify Wrapped thing because maybe they are like shy sharing like what they listen during workouts or what they listen when singing in the shower. So the privacy that we mean here is like privacy between like friends, between like partners that are matching in these dating apps. So this is like actually the diagram of this application, and I'm gonna explain it like very slowly because that's kind of the core of the whole presentation, and we're gonna come back to this like many times. There are like, first of all, like two, I hope you see my arrow. So there are like two parties, Alice and Bob, and in the middle we have like a server. The first thing happening is that Alice and Bob needs to come together with their own secret keys, secret key 1 and secret key 2 in this case, and generate a public key, a common shared public key for the application. Then let's say that they have their set of music preferences. So for like a sake of simplicity, we just consider a sort of a vector made by 1 and zeros. 1 means you like an artist, 0 means you don't like this artist, and each index in the vector corresponds to an artist. So Alice has her own set, Bob has his own set, and what they do later is that they encrypt this this set with the common public key generated before. They come up with some ciphertext, and this ciphertext is then passed to a server that will run a FHE matching engine. We're going to come to that later. And the output of this will be a a ciphertext matching score. So I think you kind of know this now after like the other presentation, I guess, but like the FHE matching engine is like a fully homomorphic evaluation performed on the ciphertext. And as you know, like the resulting ciphertext is maintaining a mapping to the plain text after the fully homomorphic encryption evaluation is performed. So in this phase, like in the middle, you see that the server is only managing ciphertext, so they don't really access any plain text data. And eventually, Alice and Bob come together. They put together their secret keys, and they are then able to decrypt this match score. And an important thing to notice here is that the only way to decrypt this ciphertext match score is that both SK1 and SK2 come together. So is there any question on this, because it's kind of really important? Good. Okay. So let's focus a bit more on the matching engine. Like, what is this matching engine is doing? So the matching engine will compute a dot product between the vectors of encrypted set A and the vector encrypted set B. And as you see, like this product will just output like 1 if both of the artists are matching. So it's a kind of a very kind of dummy matching engine that is like, okay, if you both like this artist, you're matching. If you don't, either one of you don't like this artist, no match. And it extracts a sort of a score out of it. So you see here is just like one artist is like by both out of 4. So the score is 25%. So this is like kind of the first iteration. And I think something that is important to underline here is that, of course, encryption operation is non-deterministic. I think there might be like some better formalism to define that, but like when I say non-deterministic, it's like this encryption of 1 is different from this encryption of 1 from the eye of the server. So they cannot really tell if it's like a 0 or 1. I think this is important to mention. We can also build a kind of a more sophisticated matching engine. So now we replace the artist by a set of genres, and we assign a weight for each genre based on like the preference of Alice and Bob. And the matching engine will kind of compute a sort of like a distance vector between the weights. So of course, it's like both are assigned the same weight. The distance would be 0, and this is like a good match. If one says 0 and the other say 10, that's like the worst possible match. So we subtract them, we kind of extract absolute value, and we sum together the distances. And if the result is 0, it means like perfect matching. If the result is 40, it means they are like completely at the opposite, and the matching score will be 0. And then we can become even more creative and create like matching engines that are based on deep learning recommendation or natural language model recommendation. So I don't really know how they work, but I suppose that like this is what Spotify does to give us a recommendation. And the main point of this presentation and this initial part is not like explaining you how this matching engine work, because I don't know either. But like the takeaway here is that you can become really creative with FHE in this part, in the matching engine part, and as long as you can express a function with like a arithmetic circuit, you can kind of make everything possible here. So the point is like the creativity that FHE application can kind of unleash, starting from these very basic primitives that, as you know, are like addition and multiplication. And everything, of course, would still be happening on encrypted data. So that was the end of the application part. Now we're gonna move a bit deeper into the abstraction part. So this is like simply the diagram that I explained you before, but it's more general purpose. So we no longer have like the sets of songs, but it's like data A and data B. So it's kind of can be whatever data really. The FHE engine now is no longer specific to the recommendation system, but it can be any function. And oh, of course, like also another important part to mention is that in order to allow this FHE engine to work on encrypted data, the input ciphertext must be encrypted under the same public key. And yeah, so that's basically the model that now we're gonna analyze more specifically to understand what are the requirements and what are like the benefits of building an application, an FHE application, using this kind of mental model, this kind of framework. So first of all, as I said before, I'm just gonna repeat it again. The FHE engine can be actually any arbitrary function that is encoded, is built using arithmetic circuits, and this is powerful. The CT out is a private shared state. So this is actually a cool thing that is not really possible when you build application only with like zero knowledge proof, for example. And when I say private shared state, I mean like shared because this is composed by both the state of Alice and Bob, and private, meaning that it should be accessible only by Alice, Bob, and no one else. And yeah, exactly. Like this, the party that contributed to the shared state must agree on what to decrypt. So if they put together their secret keys, then they are able to decrypt this. But for example, CTA, which is the encryption of the Alice data, should not be decryptable unless Alice agrees to do so, unless Alice kind of contribute with her secret key. So why, another question that you might have is like, why we need a server in the middle? Why can't we just cut the server out? So as you know, like the FHE computation part is an expensive part, and in terms of like computational resource. And the cool part here is that we are able to outsource this computation to an untrusted, powerful third-party server. And we don't need really to, maybe again, comparing it to ZK, there are like some applications that require stuff to happen locally on user device to not break privacy of data. But since the computation is happening on cyber or like encrypted data, we don't really care about like giving this computation to an untrusted server. And why? So what is like the condition to make it untrusted? Like how we can remove this trust assumption to the server? Like in order to do so, the FHE engine, let's say like the function that is performed by the server, must be public, must be known by anyone. And in this way, you can catch a malicious server. So you can just perform this function again because these ciphertexts are public, the function is public, and you can see if the output is actually correct. So there are like many ways you can do that. You can, I think like Zama presented before me, and they have like a consensus of nodes on this computation, or you can also make maybe some fraud proof mechanism such that you accept it optimistically and you verify it later, and you maybe add some sort of slashing mechanism on top of your protocol to penalize the server. But the requirement is that the function is public, because if the function is private and only known by the server, you cannot really tell if they're doing it correctly or not. And also another thing is that maybe also like the diagram contributes to seeing this as something symmetric, so that like the input of Alice and Bob is symmetric and the function is like working symmetrically on their input. But actually, it doesn't have to be symmetric. So it can be, I don't know, Alice that is contributing with like a song and Bob with a playlist, and then the FHE engine will work differently. So it's important, it doesn't have to be symmetric from the two parties. And since we are outsourcing the most intense part to the server, we can also see that like the operations that are performed by the individual parties have limited requirements in terms of computation and communication bandwidth, which I think, I don't know if maybe Jay explained it before, but we believe that this is something different from like most like similar application, but powered by MPC protocols that have instead like higher requirements in terms of communication bandwidth. With FHE, we have this kind of cool property that we can outsource the heavy part to a server. And as you can see, these two parts where the arrows points both to Alice and Bob, this and this in red, are multi-party protocols. So they are multi-party, meaning that require input from both parties, but they don't require parties to be live at the same time necessarily. So they can be run asynchronously. And this is based on this paper, multi-party homomorphic encryption from RLWE. And also want to mention that it doesn't really need to be two parties. It can be extended to more parties, but we tend to privilege system that where like the decryption part is like n out of n. So meaning that it requires all the parties to contribute to the decryption. And this is to avoid that an encrypted value of a party gets decrypted against their will by a malicious set of participants. So for example, if it was like 4 parties and a decryption threshold of 3 out of 4, 3 parties can potentially collude and decrypt the ciphertext of Alice even without her giving the consent to do so. But of course, if you set like an n out of n threshold with many parties, then it's kind of difficult to manage because you need like a very strong coordination requirements. And and there's also like an issue that I see here. I don't know if there's a way to solve that, but the last mover in the decryption multi-party protocol has a sort of an advantage. So they can, first of all, they can drop off the protocol and basically, the whole flow will fail if they don't join this multi-party computation. But even worse, they can perform the decryption. So they have access to the decryption performed by the first participant. They can perform the decryption using their own secret key. And they are now able to decrypt this ciphertext. So they are able to see out, but they can keep this result from themselves. So don't share it with, in this case, with the first participant. And this might be bad according to like how, like what is at stake in your application. But I think the solution is not really cryptography based, probably, but it's more application specific. So you can insert in your application some penalties if like there's a participant that drop off or doesn't contribute to the decryption according to the rules. And oh yes, that's the part where there's also another issue. So each party, Bob and Alice, needs to trust that the other party has been performing the encryption correctly. So they could just potentially, rather than passing CTA, which is the real ciphertext, they can just take any ciphertext that they find online, I don't know, anything really, and pass it to the server. So we need a way to make this kind of provable, to remove this trust, and we're going to use ZK-FHE for that. So that's the next part of the presentation, like how we can use ZK-FHE to achieve verifiable fully homomorphic encryption. And I want to underline here that like verifiable fully homomorphic encryption actually refers to the encryption function. So going back to this, verifiable fully homomorphic encryption relates to this part, not this part that is more like, let's say, verifiable fully homomorphic evaluation. So let's see, like this is again the example where like Alice is honest and she's encrypting her actual preferences. But let's consider a different scenario. Like Alice just wants to match with Bob at all costs, and she knows Bob, she knows his preferences, so she will basically build a fake set of preferences that will just lead to 100% match of Bob. So she can modify her preferences, encrypt this fake set A, and it will result with 100% preference. So how can we avoid that? How can we make this application less fragile? So the way is that, of course, this set should be authenticated somehow. So if you rely on Spotify, it should be like some data that are coming from Spotify, that are attested by Spotify, and not just something that you can enter or fake randomly. And maybe you can see that there's no like big risk in this. Like if you fake your preferences, like okay, right? But if you are building an application that has more at stake, like maybe like money transfer and stuff, you really want this kind of input of the encryption to not be faked. So we add into our protocol a proof to this action, and of course it will be also symmetrically needed by Bob as well. But what is this proof proving? The proof is proving that the set A belongs to Alice according to Spotify. So this is something more specific to the application, but you can think about like some signed data coming from Spotify, and we are proving that these data are signed by Spotify and they belong to Alice. And most importantly, we're going to prove that this CTA, this ciphertext result, is the correct encryption of the authenticated set A with the public key, which was the public key generated at step 0 as part of the multi-party protocol. So this part, as we said before, is something specific to the application. So this is not what we built. Like the application that I'm explaining you, I just thought about it yesterday for the presentation. It's not something that we are actually building, just to showcase what it means and what are like the issues. But actually, this part of the proof that is like the encryption, proving the correct encryption of something, is more general purpose and can be used by any FHE application. So that's actually what we built, and we call this the ZK-FHE gadget. This is a gadget to prove the correct encryption of some plain text message, and it specifically works for BFV scheme that, as you might know, is like one of the many popular FHE scheme available. And the idea is to take this as a gadget, as you can see, as like a piece of a puzzle that you can plug into other proofs that are more specific to your application. So something like this case, proving the authentication of the set, or it can be some state transition in a game. But the important part is that it's just pluggable. So you don't really need to worry about like your app. You just need to worry about your application specific logic. It was built using Elo2lib, that is like a fork run by Axiom of Elo2. And the most intense, the most like the biggest cost of the circuit is large degree polynomial multiplication. So we had to kind of focus on optimizing this. This is going to be a more technical part, but it's not really required to use the gadget. So just to explain you, like ideally, like the first thing that we did to perform polynomial multiplication is something like as you learn from like elementary school, like to do polynomial multiplication, just multiply element by element. So this by this equal this, etc. But this is like result in like n plus 1. Well, it's like n a o of nm complexity in terms of constraint, where n is the degree of polynomial 1 and m is the degree of polynomial 2. So how can we constrain that a polynomial multiplication is performed correctly inside the circuit while being more efficient than this? So what we did is basically, this is like the idea. So let's say that we have these three polynomials such that f multiplied by g equals h. And according to the Schwarz-Zippel lemma, if you just draw some randomness from a field and you evaluate the polynomial, the relation with this random element, if this relation holds true for this random element, there's like a really, really high probability that this is true for all the elements in the field. So what we do then is like we compute the polynomial multiplication outside of the circuit. We just assign the polynomials in the circuit. We evaluate this polynomial at a random value inside the circuit, and the constraint that we set is that like basically this relation is true when all the polynomials are evaluated at this random value, and we reduce the complexity largely. So now it's like O n plus n. Before it was O n times m. So like maybe the question is like, how can you draw randomness from a circuit? Like, you know that like all the values should be predetermined at compile time. So how can you extract randomness? For this, like the practical answer is you just use this challenge API from Elo2. But just to understand a bit more specifically how this challenge API works, is that they separate the witness generation in two different phases. And in phase one, you just commit to the polynomials. So you commit to the coefficients of this polynomial. And you extract a commitment from this column, and hashing this commitment will result in this random value gamma that you can then use in phase two as randomness to evaluate this polynomial. So this is kind of a Fiat-Shamir heuristic, because if you then want to kind of cheat in this part, you need to modify the polynomial that are passed in phase one. So it's a kind of a circle that you never solve. So these are like the benchmarks. We use this, there's like this table that is the standard for parameters in BFV. And we use like this log Q equals 29 and this security level. And we are able to generate this proof in 9.5 seconds on my laptop, which I think is really good. But there are like still open issues in this repository. And in general, I mean, of course, we're not even close to like the final state of ZK and FHE encryption. Like the main thing is that we want to support larger Q. So as you see from this table, like this is indicating, this column is indicating like the number of bits of Q. And there are like cases in which you want like a very large Q. And every time that you see a value that is beyond like 254, this is not supported by our circuit, because it will be greater than the prime of the circuit. And yeah, we cannot support that. So the idea is like to our from field arithmetic operation such that we can support larger Q. And the second open issue, I mean, this is not really an issue, it's more like a task, a practical task that is like adding proof for correct decryption. And you can see this task on GitHub, and actually this is the link for the GitHub if you want to have a look at the repo. And I also want to mention that this was like a joint work with Enrico, that is also working on this together. And yeah, I'm also happy to take any question if you have.
I wanted to know what are the cryptographic assumptions behind the PSE's speed packet.
So he's asking about the cryptographic assumptions behind the PFPs. Yeah.
Okay, right. So I mean, I don't think it's really like my skill to explain you what are like these cryptographic assumptions. So I know that like BFE is relies on the ring learning with error assumption. So this is, I think, the security assumption. But like honestly, what we did in the work is basically reading the paper of PFE and trying to implement that. So we kind of rely on what like the papers say based on the security assumption. It's not that we're like really. I'm more like an engineer than a cryptographer. So maybe I'm not the right person to answer this.
The primitives that we use are learning with errors, and that itself constitutes of ring learning with errors. And BFP uses regular learning primitives. Any other?
When can a developer use this to develop applications?
When? The question is when
Yeah.
or where?
When?
Okay. So as it's kind of so you can use it now at your own risk, and because of course it's not audited. So there are like a few limitations if you want to use it now. So of course, one limitation is this one, like the size of the queue, which is not you cannot support large queues. And the other limitation is that you need to build a circuit with the same tooling that I used to build this library, which is Elo2lib. So what we want to do, as you Jay know, is like we want to kind of start working with like maybe some other framework like Circom or general Elo2, such that it is like more pluggable for like developers. But I mean, of course, it's like not like something that is really like plug and play. But if you really want to use it like today, you can come to me and speak.
Okay. How can someone get in touch with you to this?
Maybe I can share the Telegram if anyone wants. You have any question?
Enrico, just wanted your thoughts around how efficient is this compared to just raw two-party computation between the nodes, like private set intersection, right? If we had to do taking the Spotify, for example, right?
Right. Well, okay, so it's a difficult question, and I don't know. I don't have like benchmark in hand, so it's really difficult to say. Like, it would be cool to build like the same application, same setting, using a technology and the other, and then compare what are the outputs. But like let's go maybe here. Like this abstraction. Like my intuition is that you get efficiency on the parties side. So the parties can be running this whole thing on their own devices, which is good compared to probably MPC, where there are like higher requirements in terms of bandwidth for like this two guys. But of course, you add something at the middle, which is like the server that yeah, I mean, as long as you don't have like limit in terms of like how powerful this server can be, then it's okay. But of course, comes with a cost. So yeah, I don't have like a specific answer to your question. Maybe also Jay can add something to this. Yeah.
Thank you so much, Enrico.
If anyone have any question for
Thank you, guys. Bye.
Thank you so much. Thank you so much.
Cool. I think that was the end of all the sessions that we were having. And we are having a session by Enrico to announce the hackathon winners of the hackathon. Everyone, so next we will present the hackathon projects participated to the Enrico hackathon 2 days ago. So for anyone new here, basically we hosted a 2-day hackathon where people played about the Eco, which is a EDM, fully mobile encryption. So all the applications today represent will manage some form of confidentiality fully on chain. And yeah, so we have 5 to 6 projects here for you. Basically, so everyone will be presenting here for 5 minutes.